So today we're gonna study circular motion, and the uniform circular motion means that the speed that is going around is constant. So there are many examples that I can show you. Let's see this one here. So you see, this is rotating, going around this circle, right? That's different from a linear motion where the ball would go in a straight line, right? Now, let's look at this one here. Let's see if I'm successful in this one. So it's rotating here. You guys believe it's rotating, right? When I remove the ring, what do you think is going to happen?
It'll stop rotating.
Huh?
It'll stop rotating.
It will stop rotating, and then, yes?
It would go a different direction, but it won't stop rotating.
Will not stop rotating, but will go in a different direction. Somebody said it's going straight up. So what do you think?
I think it's
It's going to be straight. Yeah. So let's try again. See if I can do. Oh, you guys see that? It's trying to go hard to. I'm going to use the small one. I don't want the big ones to fly away. Is that clear? Went straight. Why do you think it goes straight?
There's nothing holding it like in.
It's not, there's nothing making, right? Once it goes out of this boundary here, right? There is nothing that is making this ball go in circles. Let's try here again. Let's see what happens. So I'm going to try here far away from everybody. So you see it's rotating. See that? Went straight out. At some point. Again. Right. So I think it's become clear that once goes around this is free to go, it goes a straight line, right? Can we relate that to some law that we reviewed? Is that the second law, the first law? Once it's out of this circle, which law is from Newton's law? Yes?
Is it the second one?
Is what?
Is it the second one?
Second law. Once it releases from here and goes a straight line, you think it's a second law?
The first one.
Is the first law? Why do you think is the first law?
Because once it's in motion, it'll stay.
So while this is on a circle, which law are we talking about? If it's in a circle, why is going in a circle?
If the boundary is moving, like, it can only move in a circle within the boundary.
So it's restricting the movement, right? Once I remove this, the thing goes free as a straight line, right? Remember when we had the car and we give a little push, it would go continuous, right? Which law was that one? That was the first law, right? What is the first law again?
An object in motion stays in motion, an object at rest stays at rest.
Exactly. So that means once it is out of here, right? There's nothing to hold it. When I say nothing, what do I really mean?
No boundaries.
Huh? Start with F. Start with F. Oh, I'm looking for. What?
No force.
No force, right? No force. Okay. So let's see this one here now. So if I have a string and just holding a string, if I remove this weight, you see the string gets relaxed, but once I put the string, it comes down, so that means there is some force there, right? Now, let's try to rotate. Let's see what happens when I try to rotate this. What do you think is happening?
There's more force being put on the spring.
So the spring is getting, further, displacing from its equilibrium, right? So let's see if I can try this safely. You guys see it's going on a wide radius, right? So I'm going to try to reduce the speed a little bit. What's happening when I reduce the speed?
It's shrinking.
It's shrinking, right? The radius is becoming less, right? Very good. I have all this one here. So let's see. So this one, it's rotating, right? I'm going to let it go, and then it's straight. But it was not completely straight. Why? Because of gravity. In this case, there was gravity that, it didn't let it go on a straight line. You can also look at this one here and see what's happening. So what think you guys, what is happening here? Yes?
The centrifugal force is pushing the water out, which means that the air is going in, which is why the little ball thing that's floating is going in.
Right. Let's see if I can stop it. When I'm holding like that, why do you think the level of the water is flat?
Gravity.
Gravity,
Even
right.
though-
So when I start to rotate this, it's like, what's happening? What is happening? So it's like gravity now is an angle, right? So we can think like in space, there's a problem with lack of gravity. We can create gravity by spinning, right, a big circle. And by doing that, we can mimic the Earth gravity, and we can live in space. So I put an article on Canvas. I'd like you guys to read about artificial gravity. And I have a problem. At the end of the class, I'm going to show you the problem. I'd like you guys to work on that, to calculate what should be the angular velocity so we can mimic gravity in space. Wow, that's heavy, isn't it? I'm gonna put it. So now I have here a bucket with water. Believe me, I got wet at home several times trying to do this. So what do you think is gonna happen?
The water's gonna stay in the bucket if you do it fast enough.
You gotta go fast enough, right? So we're gonna try to calculate what is, the minimum velocity, right? The minimum velocity that I need in order to keep the water on the bucket. Also, on a problem on a roller coaster, right? We go on a train upside down. We need to calculate also, we're gonna calculate the minimum velocity there. Now, what do you think happens when we go up in a hill?
More force pushing down on you.
If you go with high speed, what do you think is going to happen? You go up a hill, you can fly, right? If you go to speed. So we're going to calculate the maximum speed that we can go on a hill without flying. So all those things we're going to do. Okay, so let's see if I'm successful with this. Okay. I came all dressed up today, but you never know. I tried outside, it worked. Oh. But you see, I was able to do, a couple loops, it worked. Got wet there, but,
Are you ready?
because I slowed down, right? I was this, and I slowed down. Get this dry right away. And then, so, all right, so we did some demonstrations. So now let's do some math here, okay? So definitely, what happens on a circular motion is that the velocity is changing, right? Now, the speed can be the same. The speed is the same if this is rotating, right? At a constant angular velocity. The speed, the linear speed is the same. But the velocity, the linear velocity is changing the direction. And because it's changing, there has to be what? If the speed, the velocity is changing, what is happening? It has to be
Acceleration.
acceleration, right? If it is an acceleration, then we talk about the second law of Newton. It has to be a force. So there has to be a force here. And the force is the direction of the acceleration, right? So if I have the speed going in this direction, and then on the other direction, the delta V is going to be directing to the center of this circle. All right? So the acceleration is, direction the acceleration is to the center. All right? So from this diagram here, this angle is the same as the angle of the velocity, the change in velocity. The change in the angle of the position of this ball going on the circle, right, is the same angle. But the displacement is perpendicular to the change in velocity. So the displacement is perpendicular to the acceleration. Is that okay? So the speed is the same. That means that the magnitude of the speed is the same, but the vector is different. Okay? It's the same like I have a vector A and negative A. They are different vectors, right? They have different directions. When I add them, they cancel each other, right? So we have to define some terms here. So some parameters like the period. The period is the time to complete one revolution, right? A complete rotation, like this ball is here, and it takes some time to go and come back to that same, okay, that's called, the time it takes to complete that is called period, okay? Then we have frequency. Frequency is what? Frequency is the number of rotations per second. How many rotations we're doing in a second? If I do quick enough, no, that's one rotation, right? 2 rotations in 1 second, right? So that would be the frequency. Angular velocity. So what is angular velocity? It's different from linear velocity. Linear velocity, we're talking about meters, right? Angular velocity, we talk about an angle. So it's read in radius per second, while the linear velocity is meters per second. Okay?
Wait, what is angular velocity? I couldn't tell.
Is the variation on the angle.
No, the unit.
For the unit, rising
Radian?
radians per second. Radians per second. Okay? And linear velocity is meters per second. So acceleration is the variation of velocity over time, and we see that the acceleration is perpendicular to the displacement, right? So because of this triangle is the same as this one, right, is similar, we can say that the variation of velocity is proportional to the variation of displacement divided by the R. So the radius, this divided by the radius here, is the same as this divided by this side of the triangle, right? So we come up with this relation, and from here, we could come to the formula that the centripetal acceleration is the square of the linear speed divided by the radius, okay? Now, if we want to relate the linear velocity or speed with the angular velocity, so we calculate that linear velocity is the distance, right, of the circumference, that is 2πr. 2πr is the distance, is this circumference, divided by the period, right? Because it takes so much time to complete the whole circle, the whole revolution. So omega, that is the angular velocity, is 2π, right, divided by the period. Okay? So then we have this formula here, and then we can relate that to this one. If we substitute this speed here, we square w squared and r squared divided by r is going to be omega squared times r. So this is the centripetal acceleration, okay? Now, everything above here is what we call uniform circular motion. We call uniform because the speed here is the same. Okay? This is going at a constant angular velocity. If you think about, those CDs, right? When you start the rotation, it speeds up. But once it's stabilized, it keeps moving at the uniform motion, right? But if you turn off your CD player, right, it starts to slow down, so that's being decelerated, right? It's the same thing. So what's happening is that the angular velocity is changing, the angular velocity is changing, and so the linear speed. Is that okay? The difference between uniform circular motion versus non-uniform, right? Non-uniform circular motion means that the speed, I'm putting here on the V in red because to remind you that actually here, when I have angular acceleration, so the angular velocity is changing with time, we're going to have an angular acceleration. Okay? If the angular velocity is changing with time, we're talking about an acceleration. The same way we were talking about linear speed changing with time, that meant we have an acceleration, right? It's the rate of change per time is acceleration. So the rate of change of the angular velocity with time is going to give us an angular acceleration, okay? So here, this speed is changing because it's being accelerated, right? So that means I have a tangential acceleration, tangential linear acceleration, because this speed here is also changing. So how do I relate the tangential acceleration with the angular acceleration? So the tangential acceleration is the variation of the speed divided by time, but that is omega r. I place omega r here. So the tangential acceleration is equal to the angular acceleration times the radius. All right? It's good to go through this, solving these equations like that, but remember, you guys are going to use a table, right? You can make tables, you can have all the formulas there. for you to solve the problems. You don't need to memorize all this, but you need to understand where this is coming from, okay? Now, it is important to remember that the centripetal acceleration affects what? The direction, right? That's what we call centripetal. Why we call centripetal? What does the word centripetal mean? Circular motion. Not circular motion. Yeah, it's related to circular motion, but centripetal means
Center.
huh?
Center.
Center, right? Centripetal, right? Towards the center. So it is, you see, as this thing rotates, it keeps pointing to the center, right? So the ball wants to go on a straight line here. The moment we break this line, what is the line doing to it? It's causing a tension to it. It's keeping, you know, connected to the center here, right? But once I cut this line, the tension is gone. So now this thing is free to go, right? That means the first law of Newton. Now it's free. There is no force acting on mine anymore. So now I'm free to go away, all right? But as long as I'm connected to this string, right, I'm not free, right? I have to follow this circular motion here. But once I cut the line, it's gone, right? So what I'm trying to convey to you today is that this centripetal force, right, is directing to the center, right? Now, it's good to understand also that there are many forces that can be related to this centripetal force. Right? Centripetal just means facing, directed to the center. But that could come from this example here that I showed you, right? This example here that, like this one. This thing is rotating, but it's no string, right? So it's a different, it's not a tension. There's no tension here because there's no string. Now here, I have a string, so here we have a tension here, right? So the centripetal force in this case is the tension. The centripetal force here is facing to the center, but it's not the tension, right? Where is the centripetal force coming here from?
The boundary.
Well, this boundary, there is a contact here, right? That is making this towards the center. What about a satellite that is moving around, the Earth? There's no string attached to it. It's a gravitational force, right? Like here, this example. I have the Earth here, I have a satellite, so we talk about gravity force here, right? That is causing this to keep falling, right? So it moves a little this direction, but then the force brings you back. It moves again and brings it back, right? It's trying to move straight, but it brings back the force. So the centripetal force here would be Fgmm divided by r squared. Okay. Here we have a spring. We have a force, right, that is making this thing go down, right? Balance out with the weight. This force depends on a constant of the spring, right? If the spring is loose, it goes further, right? And the distance. Okay, we can calculate the force right now, of the spring. It's the same as the weight, but this is proportional to a constant of the spring. Okay? All right, so, also on a tornado, right, a particle that's going around, you know, there's no string attached to it, but it's still going around, right? All right, so let's try to do this experiment now. Now, so what is this experiment? Experiment, we have two masses. One is connected to this string here, and we have this little tube. Okay, and here I have another mass, and what I'm going to do, I'm going to try to rotate this. So do you see that it's not completely horizontal, right? It has an angle there, right? It's very hard, and if I slow down, it hits even my hand, right? It slows down, right? But I have to increase. As I increase the speed, what's happening is becoming more and more horizontal, okay? So let's take that. Now, if the velocity, if this goes really fast, I can just make the tension here equal to the centripetal force. Right? So the centripetal force is the centripetal acceleration, right, times the mass. So the centripetal force, this is the centripetal force. This is the acceleration that we just calculated here, okay? So now, because this, we have a weight here, we have a tension. This tension is the same as this weight, and it goes through here and there. Now, this radius and the speed is going to give us the centripetal force. Centripetal force is not changing. But if I change the speed, the radius is going to change. And it's that relation that we're going to try to measure, right here. The period, and if we measure the period, we calculate the angular velocity. If we know the angular velocity and we measure the radius, we calculate the linear speed, and with the linear speed we calculate the centripetal force. Now the centripetal force has to be equal to the mass here on the bottom times g, right? The mass times g is the force here going down. The centripetal force needs to be equal to that. Is that clear? Of course, there's some friction here that is going to, you know, make this a little harder, but you know, let's try to see. I did this several times at home, about 20, and the best result I got was like 4%. So this one here is related to 100 grams. I have here 100 grams and 20 grams. This one here is 20 grams. So I'm going to need a volunteer. We have a volunteer? So I need you to take the time. First practice a little bit with the this, and then turn it on and turn it off. And you're going to have to time 10 revolutions, okay? 10 revolutions. You look at one point and I let you know when I feel it's like stable. It's hard to get that done, but I'm going to try my best. Once I think it's stable, I say, go ahead, and then you fix this one position and count 10 times in that same position, okay? And then I'm going to stop, try to hold this, and then you're going to measure this distance because this is going to be the radius, okay? So let's see if I can get it. Okay, we can try now.
6 seconds.
How long?
6 seconds.
6 seconds. Okay, so let's measure this radius here. Distance in centimeters.
So you had, 83 centimeters.
83 centimeters. So let's write that down here. So that was 6 seconds. And then you said 80 centimeters.
83, yeah.
83. That's pretty, a big difference here. Let's try to measure, and I felt that, you know, at some point, it got off a little bit. Okay, let's try to measure again. If we get, this is close enough, this was close enough, but here, we have a little gap. Let's see if I can get it again. Okay. Okay, so let's measure the distance.
You got 70?
70?
Yeah.
Okay. Let's see what we got. So that was 70, so that's 0.7. And you said was what?
6.57.
6.57. Okay, so let's do it like that. That's okay, thank you. So let's do the calculation now. So this is 10 revolutions. What is the period? This is the time for 10 revolutions. What would be the period?
0.6.
Huh? 0.6, right? So if the period is 0.6, what's going to be the angular velocity? Can you guys calculate? Do you have a calculator? What is the formula? What is the formula to calculate angular velocity? It's here somewhere. It's here somewhere. So you can find the formula somewhere here and give me a number. Did you get the number?
10.46.
10.46, okay, very good. 10.46,
But shouldn't it be the same as the one above?
huh?
Shouldn't it be the same as the one above it? Shouldn't it be 10.52?
Well, this is, you see, this is like approximation, right? So I have here 5.9, this is different from this number. It's because it round up here, I round up. So if you use these numbers, you're gonna get 5.2, okay? Now, this here is, the radius is 0.83, so we have to calculate the speed. What's gonna be the speed? The speed is going to be angular velocity times the radius, right? So we have here angular velocity, we have the radius, so what's going to be v? Can you calculate that?
8.6.
How much? 6.6?
8.6.
8.6. So now I have v, I can square that, I can divide it by r, and multiply that times, which m should I multiply?
M2.
M2?
No M1 because it's the one
Yeah, M1, right? Because M1, what is M2? M2 is this guy here. What is M1? M1 is this guy. This is the one that is rotating, right? Going around like this. So this is the one that we use for the centripetal force. So can you come up with a figure here so I can calculate that here?
0.7.
How much?
I got 0.7.
0.7?
Yeah.
Is that correct?
I got 1.78.
1.78? Yeah, that looks more. 1.78. And then I have here 98. So that's a bigger error there, right? So I'd like you guys to calculate at home for these two values here and calculate the error too, okay? You calculate the error by subtracting this and divide it by 9.8. So you have the error there. Okay. So let's move on now to this problem here. So let's see if we can solve this problem. What is, I'm asking, let's calculate the normal force here. Okay, what is the normal force?
Mass times acceleration.
So if I have a book, let's say a book on the table, like this, what is the normal force?
Gravity.
No, it's 0.
Yeah, we have gravity here is mg, but we have what we call a normal force, is a contact force that keeps the book from continue going down, right? So that's the normal force. So what would be the normal force here? So in order to solve this, we need to create a force diagram. What's the force diagram going to look like? We have gravity, right? The weight, let's say this here is MA, right? M, right? This is a box. The box has M equals to, let's say, 5 grams, okay? So this box is traveling here, and it comes to a point A, and then goes up, comes to a point B, right? And I'm asking, let's calculate the normal force here, and the normal force here. Okay? So, do you think it's going to be different? Is the normal force going to be different here and there, or is it going to be the same? Different. Why do you think it's going to be different?
Because it's going faster as it goes down, but as it goes up, it slows down.
Okay. In order to have a curve, any curve motion requires some force, right? So here, we're going to have a force this way. And when it goes this way, right, up, we're going to force the other direction. So that is going to unbalance the normal force, okay? So, so when I have this here, I of course I'm going to have my weight here, my mg, gravity, and I'm going to have m, right? M, my normal force. And acceleration here is going in which direction on point A? Which direction is my acceleration going?
Down.
Where is the curve the curve is the circular. What is the acceleration at this point? The centripetal acceleration. Where is the centripetal acceleration going on this point?
Is the object moving or
Huh?
is the object moving?
Towards the middle, right? Acceleration is going towards the middle, the center of the curvature, right? So at this point, the centripetal acceleration is going towards the center. As it keeps moving, rotating like this, where is the acceleration now? Going in this direction. And if it keeps going down, at this point, where is the acceleration going to? Up, right? So here, it's like I have a radius is this way. So let's say R here. I have a radius there. And let's say that radius is 2 meters or whatever. Let's say R is 2 meters, okay? 2 meters. So this thing is like having a circle here. Right? Like having a circle there. So at this point, the acceleration is going up. So here we have AC going up. Okay? What about point B? Let's do the force diagram for point B. What's going to happen here at point B? This is point A. This is point B. We're still going to have gravity here, and we're going to have a normal force. But where is the acceleration at point B? Where's the direction of the acceleration at point B? So, if this is the center of this here, right? Acceleration at this point is going down. Okay? All right? So the strategy to solve any of these problems is, what is the first thing you guys need to do?
Draw a picture.
Draw this picture, right? And then you need to draw a force diagram, okay? There's a strategy. If you use this strategy, you know, you're going to be successful to solve any kind of problem. Because they're all basically the same, okay? Identify the forces acting on our system here. Our system here is the box, right? Identify the force, draw the force diagram, draw force diagram, okay? And then, what? Apply the second law of Newton. Where is the second law of Newton? First, draw, and then second law of Newton. What is that? What is second law of Newton? The sum of forces so we have here the y direction, right? The y direction. So the sum of forces on the y direction will be equal to what? So the normal force mg, okay? And this is equal to what? M centripetal force and mg, okay? Now, I want to calculate n, so n is going to be equal to mg okay? So this is for point A, okay? Now for point B, we do the same thing, the sum of F on the Y direction. In this case here, G is gonna be greater than N, right? And so N is going to be M V R minus mg, okay? So from here we see that the normal force on the hill is going to be less than on point A, okay? That's why when we go up the hill we feel like, you know, we go weightless, right? So if I want to calculate the maximum velocity that I should go on the hill, what should I do? How can I calculate that? How do I calculate the maximum velocity? Maximum speed here on the hill. So I don't fly away, right? Do you guys see that if I go too fast here, I'm just going to all the way up there? Do you guys see it? Right? And you guys ride a bicycle and then you go up the mountain and then if you're too fast, just fly away, right? But if you reduce your speed, you are able to go around, right? And there is this maximum speed that you know you can calculate here. What do you think should be the normal force? The normal force is this force of contact here, right? So if there is some contact, if you lose contact, what happens? You just fly away, right? You need to have contact all around. If you don't have the normal force here, then you're going just to slide down due to gravity, right? But so what should be the normal force for you to calculate the maximum speed you can go? What do you think? Huh? Who said that? Yeah, 0, right? So if I make the normal force 0 here, that is going to give me the maximum speed I can have. So let's do that and see what happens. If I make n equal to 0, so the normal force equal to 0, we're going to have this equal to mg. So it's going to be v squared over r equals to g. So v is going to be square root of gr. Okay? All right. Now what happens here now? Here, the normal force is going down, the weight is going down, and the centripetal is going down. Okay? So I'm going to have MAC equals mg plus n. Okay? So n